All right, welcome. Today, we are jumping into one of the most powerful tools in all of calculus, the chain rule. We're going to break it all down with some super clear examples and intuition, all coming straight from James Stewart's legendary textbook.
And just so you know, all our information for this explainer is pulled directly from section 2.5 of this very book. So if you want to go even deeper, you'll know exactly where to look. So let's get started with a little puzzle. We're going to look at a function that seems pretty simple on the surface, but as you'll see, our usual tools for differentiation can't quite handle it.
Okay, take a good look at this. How would you, yes you, find the derivative of the square root of x squared plus 1? Just think about the rules you already have in your toolbox. Does this really fit nicely into any of them?
I mean, so far in our calculus journey, we've got some heavy hitters, right? The power rule, the product rule, the quotient rule. But this problem, it's different. We've got one function, the x squared plus 1, literally nested inside another function, the square root. It's pretty clear our current toolkit is going to need an upgrade.
So, the key to solving this, the big aha moment, is to stop seeing it as one single function and start seeing it as a composition of functions. Think of it like a chain of events.
And this kind of structure has a name. It's a composite function. It's kind of like a mathematical assembly line. You take your starting value, x, and you put it through the first process, g. Then, whatever comes out of that goes immediately into the next process, f. The final result you get is f of g of x.
Okay, so let's use this idea to break down our original puzzle. We can pretty easily spot an inner function. That's g of x equals x squared plus 1. And that leaves us with an outer function, f of u equals the square root of u. And just like that, by splitting it up, we've turned one really tricky function into two much simpler pieces that we already know how to differentiate.
The textbook has this absolutely brilliant way to think about this intuitively. Remember, derivatives are all about rates of change. So, just imagine, if one thing changes twice as fast as another, and a third thing changes 3 times as fast as the second, doesn't it just make perfect sense that the third thing changes 6 times as fast as the first? The rates just multiply. And that, right there, is the core idea of the chain rule.
So that's the intuition. But how do we turn that idea about multiplying rates into a formal mathematical rule? Well, let's pull back the curtain and look at the tool that does exactly that.
And here it is, in its two most famous forms. Over on the left, you've got Leibniz notation. I love this one because you can really see the rates multiplying. It almost looks like the do's cancel out. On the right, there's prime notation. This one gives us more of a procedure. Take the derivative of the outer function, leaving the inner part alone, and then multiply by the derivative of the inner function. They're just two ways of saying the exact same powerful thing.
So this all gives us a really practical workflow that you can call the outside-in method. It's a simple, repeatable 4-step process. First, you identify your outer and inner functions, then differentiate the outside part while keeping the inside part untouched. Step 3, differentiate the inside part. And finally, just multiply those two results together. That is the chain rule in a nutshell.
Okay, theory is great, but let's be honest. The best way to really master a tool is to actually use it. So let's get our hands dirty and put the chain rule to work with some examples.
Let's start with our original puzzle. First things first, it's always a good idea to rewrite that square root as a power of 1/2. Now, applying our method, we differentiate the outside power function. That gives us 1/2 times our inner function raised to the negative 1/2. Then we just multiply that by the derivative of the inside part, which is simply 2x.
And now for the satisfying part. We just simplify it. The 1/2 and the 2 cancel out perfectly, and that negative exponent just moves the whole term down to the denominator. And there it is, our final answer. Puzzle solved.
Okay, pay attention here because this is probably one of the most common mix-ups people make. These two functions look so similar, right? But their composition, their inner and outer parts are completely different. For sine of x squared, the inside is x squared. But for sine squared x, the inside is sine of x. Getting that first step right is absolutely crucial because as you can see, it leads to two totally different answers.
Now this is where the chain rule really flexes its muscles. Differentiating something to the 100th power looks absolutely terrifying. But with the chain rule, it's a piece of cake. Seriously. You just bring the 100 down, reduce the power to 99, and then multiply by the derivative of what's inside, 3x squared. It's that simple. Amazing. And what's really cool is that the chain can have more than two links. Here we've got a function inside a function, which is inside another function. But the process is exactly the same. You just work from the very outside in, taking the derivative of each layer one by one and multiplying them all together as you go.
So, why do we spend a whole section on just this one rule? What makes it so incredibly fundamental to calculus and pretty much everything that follows? Let's zoom out and look at the big picture. Here's the thing. The chain rule isn't just one more formula to memorize. It is the key that unlocks our ability to analyze how the real world works, because most things in the real world are complex systems made of composite functions.
And you can see its power everywhere. In those classic related rates problems, it's what connects the changing volume of a balloon to its changing radius. In physics, it's the link between position, velocity, and acceleration. In economics, it shows how one small change can ripple through an entire market. It is truly the mathematics of how things are connected.
Ultimately, the chain rule gives us the power to see how a change in one part of a system causes a change in another. It's the tool for understanding domino effects, ripple effects, and chain reactions. So the real question isn't just about passing your next exam. It's about what complex system out there in the world you will understand with this tool.